Hello, I am Heeyeon Kim from KAIST, Department of Industrial Systems Engineering, DISL-LAB. Today, I will be presenting a review on the paper on Towards Lossless Dataset Distillation via Difficulty-Aligned Trajectory Matching, ICLR 2024. Before diving into the details of the paper, let's first take a look at what dataset condensation is. Dataset condensation, also known as dataset distillation, is a training set synthesis technique for data-efficient learning. It learns to condense large dataset into a small set of informative synthetic samples for training deep neural networks from scratch. The following images are examples of synthetic images, which are generated through dataset condensation from the CFAR10 dataset. The original dataset consists of 50,000 images, with 5,000 images for each of the 10 classes. The new synthetic set was generated with either 1 or 10 images per class, as shown below. The goal of dataset condensation is for the model trained on 50,000 images, as shown on the left, to achieve similar performance to a model trained on just 10 or 100 images, as shown on the right. Dataset condensation techniques can be categorized into 4 main approaches. The first is meta-model matching, which ensures that the performance of a model trained on the large original dataset is similar to that of a model trained on the condensed synthetic dataset. The second is gradient matching. This technique generates a synthetic set by reducing the distance between the network trained on the large dataset and the one trained on the synthetic dataset. The third is trajectory matching, where the synthetic set is created to follow the training trajectory of the model trained on the original dataset. Lastly, distribution matching focuses on making the data distribution of the synthetic set similar to that of the original dataset. I will now introduce the paper Towards Lossless Dataset Distillation via Difficulty-Aligned Trajectory Matching, which advances the third technique, trajectory matching. Now, let's take a closer look at trajectory matching. Before diving into this paper, let's first take a look at its predecessor, dataset distillation by matching training trajectories. The objectives of this prior work are as follows. To directly replicate the long-range training dynamics of networks trained on real datasets. To align segments of parameter trajectories trained on synthetic data with pre-recorded trajectories from models trained on real data. To overcome the limitations of synthetic datasets, which are often short-sighted and challenging to optimize. Now, let's go over the key steps of dataset distillation by matching training trajectories. First, a set of models is trained from scratch on the real dataset, and their expert training trajectories are recorded. These trajectories serve as the ground truth for the distillation process. Next, a new model is initialized with a random time step from a randomly chosen expert trajectory. This allows the process to start at different points of the training path. Then, this model is trained for several iterations on the synthetic dataset. After that, the synthetically trained network is evaluated based on how far it deviates from the corresponding expert trajectory. The further the deviation, the higher the penalty applied to the synthetic data. Finally, the penalty is backpropagated through the training iterations to refine the synthetic dataset. Through this process, MTT effectively transfers knowledge from many expert training trajectories to the distilled images, ensuring they capture the critical patterns of the original dataset. This algorithm summarizes the process we discussed earlier. Now, as we've reviewed the preceding paper, let's look at some shortcomings of the MTT method. Deep neural networks tend to learn easy patterns early in training and harder patterns later. However, previous studies conducted trajectory matching without considering this aspect. To address this, the paper conducted an experiment to analyze the effect of matching trajectories from different training phases. They trained expert models for 40 epochs and divided their training trajectories into two parts. Early trajectories, covering theta t star, where the range of t is from 0 to 20. And late trajectories, covering theta t star, where the range of t is from 20 to 40. The distillation was then performed by matching these two sets of trajectories under various IPC settings using the CFAR-10 dataset. This experiment allowed the authors to examine how different phases of training trajectories affect the effectiveness of the distillation process. The graph above shows the accuracy at each iteration for distilled CFAR-10 across various IPC settings. When the synthetic dataset is small, matching early trajectories proves more effective, as the distilled data contains easy patterns that are better suited for smaller sets. However, as the size of the synthetic dataset increases, late trajectory matching yields better results, as it introduces harder features that are more advantageous for larger sets. When IPC is low, such as 10, matching late trajectories results in poor performance, as the synthetic dataset struggles to learn harder patterns. Conversely, when IPC is high, such as 2000, matching early trajectories consistently undermines the performance, as easy patterns are insufficient for larger datasets. This demonstrates that simply matching all trajectories is not an effective strategy and requires a more tailored approach. To be specific, in low IPC settings, the capacity of distilled data is very limited, allowing only easy patterns to be distilled. However, in high IPC settings, the capacity is sufficient to distill both easy and hard patterns. To ensure dataset distillation remains effective across both low and high IPC cases, we must calibrate the difficulty of the generated patterns appropriately. Synthetic datasets can be enhanced by incorporating soft labels, which boost performance. However, existing methods fail to optimize these soft labels during distillation, leading to inconsistencies between synthetic data and the labels. DATM addresses this by introducing solutions to tackle mislabeling and instability, ensuring more effective and stable distillation. Now, let's move on to the methodology presented in this paper. The difficulty-aligned trajectory matching method adjusts the difficulty of the generated patterns by restricting the range of trajectory matching. The process works as follows. The expert trajectory is represented as theta t star, where t is from 0 to n, covering the entire training range. A lower bound t- and an upper bound t+ are defined to control the trajectory segment used for matching. The full expert trajectory is divided into three regions. To easy, where t is from 0 to t-. These represent the early training stages, which focus on very basic, easy patterns. Matching range, where t is from t- to t+. This is the range selected for trajectory matching, balancing easy and hard patterns based on the dataset's needs. To hard, where t is from t+ to n. These represent the later stages of training, where the patterns become increasingly complex and harder to learn. This restriction allows the DATM to effectively calibrate the difficulty of patterns, making the distillation process more adaptive to the dataset's requirements. Next, the DATM introduces reliable soft labels to enhance the distillation process. Soft labels are initialized using logits Li, which is equal to f theta star xi from a pre-trained model f theta star. However, these labels may be incorrect if the target class does not have the highest logit score. To address this issue, the DATM takes the following steps. Filter correctly classified samples. Sift through D-reel to identify samples correctly classified by f theta star. Subset construction. Use these correctly classified samples to construct a subset D-sub. Subset sampling. Randomly select samples from D-sub to initialize the synthetic dataset D-syn, which is consisted of xi and yi hat. Yi hat means the softmax value of Li. This process prevents distillation from being misled by incorrect labels, ensuring the soft labels are more reliable and consistent with the synthetic data. Next, DATM introduces the sequential generation strategy to address instability during distillation. When IPC is low, optimizing soft labels increases instability because smaller synthetic datasets struggle to provide proper training trajectories. This results in high and unstable distillation loss. Moreover, fragile soft labels amplify this instability due to the mismatches during the distillation process. To resolve these issues, DATM implements the sequential generation strategy. In the early distillation phase, only easy patterns are generated. As the surrogate models learn these easy patterns well, harder patterns are gradually included. This approach helps surrogate models better match expert trajectories, significantly improving stability and reducing errors during the distillation process. In the sequential generation strategy, easy patterns are generated during the early stages of distillation by applying a floating upper bound T to the sampling range of T. Initially, the value of T is kept small, and it progressively increases over time, eventually reaching its maximum value T+. The star parameters theta T star are then sampled from a uniform distribution over the range T- to T+, where T gradually approaches T+. This process ensures that only easy patterns are generated at the beginning of distillation, allowing the model to learn simple features first. As the training progresses, harder patterns are gradually introduced, enabling the model to adopt and learn more complex features over time. The process of difficulty-aligned trajectory matching consists of the following steps. First, parameters are sampled from the expert trajectories. Specifically, theta T star is selected as the starting point, and theta T plus M star as the target point of the trajectory. Next, in the trajectory update step, the intermediate parameters theta T plus N hat are computed iteratively using the trajectory update equation as follows. Afterward, the matching loss is calculated to evaluate how closely the trajectory aligns with the expert trajectory. The loss is defined as follows. This loss is then backpropagated to compute the gradients needed for optimization. Finally, in the synthetic data update step, the gradients are used to update the synthetic data xi and the logits li, where each data label pair xi, yi hat belongs to the synthetic dataset D-syn. By iteratively performing these steps, the DATM ensures that the synthetic data aligns with the expert trajectories, improving the effectiveness of the distillation process. This algorithm summarizes the process we discussed earlier. Next, let's move on to the results of the experiments conducted in this study. In the main experiment, the proposed method was compared against several state-of-the-art dataset distillation methods, including DC, DM, DSA, and others. The experiments were conducted on popular datasets such as CIFAR-10, CIFAR-100, and Tiny ImageNet. For distillation, the models used were a 3-layer ConvNet for CIFAR-10 and CIFAR-100, a 4-layer ConvNet for Tiny ImageNet. In cross-architecture experiments, the distilled datasets were evaluated on a variety of architectures, including LeNet, AlexNet, VGG11, and ResNet 18 to assess the generalizability of the method. The ATM achieves superior performance compared to most prior works across various datasets and settings. As shown in the table above, the ATM outperforms other methods with the same network architecture in nearly all cases, except for CFAR10 with IPC1. A key limitation of previous methods is that their performance improvements quite quickly saturate as the distillation ratio approaches 20%. For instance, on CFAR10, most prior methods perform similarly to, or even worse than, random selection when the ratio exceeds 10%. In contrast, the ATM remains highly effective even in high IPC scenarios, thanks to its difficulty alignment strategy. It not only achieves superior performance, but also demonstrates lossless distillation, surpassing the performance upper bound. Notably, the ATM successfully distills CFAR10 and CFAR100 to 1/5 of their original size and tiny ImageNet to 1/10, all without causing any performance drop. The ATM condensation results show superior performance across various network architectures when compared to coarser methods like random, glister, and forgetting. On CFAR100, in particular, AlexNet demonstrates a greater improvement compared to ConvNet. This highlights how higher IPC settings help alleviate the overfitting issue commonly observed in synthetic datasets during distillation. Now, let's look at the ablation studies on soft labels to evaluate their role in dataset distillation. The objective of this experiment was to determine whether soft label information could be directly integrated into distilled datasets by assigning soft labels to datasets distilled by FTD. The results show that directly assigning soft labels negatively impacts performance in small category problems. However, for datasets like CFAR100 and Tiny ImageNet, this approach provides a slight improvement to FTD. The ATM, on the other hand, significantly outperforms FTD. This is because the ATM continuously optimizes soft labels during the distillation process. This optimization ensures better consistency between the synthetic data and the labels, leading to more reliable performance across various settings. This demonstrates the importance of not just assigning soft labels, but actively optimizing them to align with the synthetic dataset. The ablation studies also reveal the impact of the teacher model's capacity on soft labels. The information contained in logits varies depending on the capacity of the teacher model, which initially affects the performance of the synthetic dataset. However, by optimizing soft labels during the distillation process, this performance gap are eliminated, significantly reducing the need for careful model selection. On the other hand, unoptimized soft labels introduce instability and lead to poor performance. This is because they increase discrepancies between the training trajectories of the synthetic dataset and the original dataset, highlighting the importance of continuous optimization to ensure stable and effective distillation. Let's now discuss the ablation studies on synthetic data initialization and its impact on the distillation process. The strategy used in the ATM involves initializing synthetic datasets by randomly sampling from a subset of the original data that contains only correctly classified samples, rather than sampling from the full dataset as done in random selection. By focusing on correctly classified samples, this approach ensures that the selected data are relatively easier for deep neural networks to learn. This strategy provides significant benefits. It accelerates convergence during the distillation process as the model can more effectively learn from easier examples early on. Additionally, it serves as a distillation speedup technique, helping to bridge the performance gap over time. This makes the distillation process not only faster, but also more effective in achieving high-quality synthetic datasets. Next, let's explore some extensions of the ATM. Let's now look at the visualization of synthetic images from the CIFAR-10 dataset with IPC50 optimized over 1,000 iterations by matching early and late trajectories. In this experiment, the early trajectory corresponds to t from 0 to 10, while the late trajectory corresponds to t from 30 to 40. The results reveal distinct differences between the two matching approaches. When matching early trajectories, the distilled images tend to lose finer details of the target object, resulting in blurred shapes. Additionally, the colors of the objects often change more drastically, as the focus is on capturing basic, easy-to-learn patterns. In contrast, matching late trajectories produces distilled images that retain more fine details and exhibit higher fidelity to the original dataset. This reflects the focus on harder, more intricate patterns during the late stages of distillation. This visualization highlights how trajectory selection affects the quality and detail of the distilled dataset, demonstrating the importance of aligning trajectory matching with the desired dataset characteristics. Now, let's look at the visualization of synthetic datasets distilled with different IPC settings. When the IPC is extremely low, the synthetic images are simplified to contain only basic color and shape information. This simplification is beneficial for networks as it focuses on easy patterns, helping them effectively learn simple features. As the IPC increases, the synthetic images become more detailed and retain more of their initialization characteristics. This reflects the model's ability to distill and preserve more complex patterns as the capacity of the synthetic dataset grows. This visualization demonstrates how the IPC setting influences the structure and complexity of the distilled datasets, showing a progression from basic to more intricate patterns. Let's discuss the distillation cost as is illustrated in the graph for CIFAR-10. The results show that optimization with higher IPC converges in fewer iterations. This is because scaling dataset distillation to higher IPC settings benefits from late trajectory matching, which minimizes the challenges needed in the images, leading to faster convergence. For example, when distilling with IPC 1000, the process requires optimizing 20 times more data compared to IPC 50. However, the actual cost increase is minimal, at only 1.05 times higher. This demonstrates the efficiency of the method as it scales well with increasing IPC while maintaining reasonable computational costs. Let's take a look at the distillation backbone networks used in the experiments as shown in the table. Dataset distillation on CIFAR-10 was performed using CONVNet and ResNet-18 across various IPC settings, followed by evaluations on diverse architectures to assess generalizability. The results highlight a key difference between the two networks. CONVNet excels in low IPC settings due to its lower capacity, which focuses on generating easy patterns. These patterns are simpler for deep neural networks to learn, making it highly effective for small synthetic datasets. In contrast, ResNet-18 performs better or matches CONVNet in high IPC settings, where harder patterns become more important for performance. This higher capacity enables it to handle the complexity of larger synthetic datasets effectively. This comparison underscores the importance of aligning the distillation backbone with the IPC setting to achieve optimal results. Finally, let's move on to the conclusion of this work. To conclude, this paper introduces the first distillation method that surpasses the performance of a model trained from scratch on the full dataset. It clearly identifies a key issue in dataset distillation. Performance does not increase proportionally with IPC, and attributes this to the incomplete learning of dataset patterns. To address this, The authors conduct a detailed analysis of the patterns used for distillation at each IPC setting. They leverage the property that models learn easy patterns early and hard patterns later, implementing a novel approach that divides the distillation process into early trajectory matching and late trajectory matching. As a result, the proposed method achieves superior performance, demonstrating its effectiveness across a variety of settings. This paper is a strong example of a well-structured study, from problem definition and cause analysis to the proposal of practical and impactful solutions. Thank you all for listening to my presentation.